So the third speaker in our session today is Dr. Hannah Felmer, who's in the School of Psychology at the University of Queensland. Hannah uses non-invasive brain stimulation methods to probe the neural mechanisms that govern perceptual and cognitive functions, and she's going to present her recent work that uses brain stimulation, imaging, and computational modelling to understand actually a classic phenomenon in the decision-making literature known as the speed-accuracy trade-off. Hannah.
Thank you very much. Thank you very much, and thank you to Jason DeGraan for inviting me to be part of this symposium. Thank you everyone for attending on the last day. It's unfortunately also my first day because my kids have had flu all week, so I'm sorry to have missed what seems to have been a really great conference, but it's lovely to be here today. So I'm going to be talking to you about some of the work we've been doing over the last few years looking at a particular form of decision strategy, which Jason already gave a nice mention to. So that's the speed-accuracy trade-off. So for anyone who's not familiar with this effect, it's exactly what it says on the tin, basically. So there is inherently a trade-off between how fast and accurate we are with our responses. I am also having clicker issues. Try the mouse. Okay, so to give a couple of real-world examples of this, we might be, for instance, driving our car, and maybe we're just driving to a school drop-off or getting some groceries. We'll probably take it pretty slow and steady and focus on accuracy of our driving. But maybe somebody's having a medical emergency in the car. We might adjust that strategy and we might put our foot down a little bit. Alternatively, we might be playing hide and seek. Maybe we don't have very long. The counter is going very fast. We just have to run behind a curtain or behind a cushion. Or maybe our counter is going nice and slow and we've got time to hide ourselves properly. So I'm sure we can think of lots of examples of this in everyday life. But today I'll talk to you about some of the work we've been doing in the lab, not involving games of hide and seek, unfortunately, looking at the speed accuracy trade-off. So I'll run through a bit of background on that, a little bit of work we've done using non-invasive brain stimulation in this field, and talk you through a series of studies that we've run to use causal approaches, which was also introduced quite nicely already by Christian, and also look at, of course, because this is an imaging conference, some 7T work we've been doing as well. So traditionally in the SAT literature, we'll use a task, something like a dot motion task, where we will give a patch of dots that will be moving, a portion of the dots will be moving coherently to either the left or the right, and participants just have to make a decision which way those dots are moving. What we often do is give them some sort of cue at the start of the trial, and this is often the cue stays the same for blocks of trials, where we tell participants to focus on speed or to focus on accuracy or to try and balance the two. So we just explicitly tell them to manipulate their speed accuracy trade-off. One of the nice things about these tasks is that we can threshold them at baseline, so we can make sure every participant is at around the same accuracy level before we start the main task. And another nice feature of this task is that we can use computational modelling to deconvolve reaction times and accuracy into latent decision processes. So very briefly, we can use models such as the linear ballistic accumulator, or LBA, or the drift diffusion to deconvolve those performance data into what we think is going on at a decision level. So the two key decision parameters that we're interested in here are caution, which is also sometimes referred to as threshold. So that's the amount of evidence we need to make a decision. And also evidence accumulation processes. So that's how much evidence we are accumulating or how fast we're accumulating evidence towards the different response options. So in this case, whether the motion was leftward or rightward. We can also look at the difference between those two accumulators to work out how high quality that evidence is, how much difference there is between the correct and the error accumulator as well. And generally in the literature, the SAT has been associated predominantly with caution effects. So this is quite easy to conceptualize. If you know you have to be fast, you'll lower that caution. You will respond with less evidence when less evidence has been reached. If, on the other hand, you don't have so much of a time deadline, you're focused on accuracy, you increase your caution, you'll take longer, you'll gather more evidence. There have been effects reported in the literature to do with drift rates as well, but caution does seem to be the factor that's most consistently found to be involved. So previously, imaging work has associated a few key regions with the SAT. The pre-supplementary motor area, otherwise known as the pre-SMA, certainly seems to be one that pops up with functional imaging. Also, our ability to flexibly adapt our caution level is associated with connectivity between the striatum and the pre-SMA. And prefrontal regions, particularly the left prefrontal area, seems to also relate to caution levels. But this evidence is correlational, which is not to say it's not good, but it is correlational. And as Christian pointed out, it is really nice to use causal techniques to support this. Also, the previous literature, particularly that relating the track strength between the pre-SMA and the striatum, had pretty small sample sizes. So it looks like a nice convincing correlation, but it had about 7 participants in it, I think, that analysis. So we wanted to use brain stimulation, and we chose transcranial direct current stimulation, which our lab does a lot of work with. I'm sure there's been quite a lot of talk about brain stimulation from what I can see of the conference program, so I'll keep this very short. But tDCS generally involves 2 electrodes, a positive terminal and anode and negative terminal cathode, placed on different parts of the head. Generally, you have one over your area of interest and another over a reference area, so an area you don't think is particularly involved in the task. And you just use it usually over 10, 20 minutes, can be before, can be during a task, to just subtly vary how the bits of brain underneath the electrodes are functioning. There's still a lot of debate as to exactly what tDCS does, how it does it, but generally it's conceptualized as modulating cortical excitability. And different effects are associated with anodal and cathodal stimulation, so the polarity seems to matter. But the nature of those effects is quite complicated. They interact with things like stimulation intensity and duration. Okay, so moving on to the studies. First of all, we started a number of years ago to see if we can use electrical stimulation, like tDCS, to modulate decision strategies. So we used a dot motion paradigm, very much like the one I just described, where the fixation colour indicated the SAT instruction participants had to use. So red was focus on accuracy, green was focus on speed, and orange was try and balance the two. We used an offline cathodal tDCS paradigm at 0.7 milliamps, which is quite typical for the field. It lasted for 20 minutes, and we used 5 by 5 centimetre electrodes. We had 2 different groups of participants. One, we targeted the left prefrontal cortex, and one we targeted the SMFC, which is broadly including the pre-SMA. But because tDCS affects a larger region of the cortex, we call it the superior medial frontal cortex here. Both of those groups had the same reference site, so the anode went over the right orbital frontal cortex in both cases, and both groups came in for 2 sessions, 1 active and 1 sham, order counterbalanced across participants. So in the absence of stimulation, so just for that sham session, we saw exactly what we expected, so a really nice effect of instruction on response caution. So for accuracy-focused conditions, caution was higher. For mixed, it was in between. For speed, it was lowest. And there was no real effect on discriminability, which is what we expected with this paradigm. For stimulation, we found a very, very clear dissociation between the 2 regions we targeted. So on the left, you can see the difference in caution between active and sham overall collapsed across instruction condition. So prefrontal cathodal tDCS seemed to increase caution overall, and SMFC stimulation seemed to decrease caution. And that graph in the middle, unfortunately, I seem to have cut off the x-axis, but it shows the same thing but broken down for the 3 instruction conditions. So accuracy on the left, mixed in the middle, and speed focused on the right. So you can see, particularly for that, well, for both of the effects were largest for the accuracy focused condition, less so for the mixed and the speed focused. We also found a little bit of a difference in discrimination, so that's the difference between the correct and the error drift rates. Particularly for the SMFC increasing this discriminability. This effect we have replicated, particularly the SMFC effect, we have replicated multiple times across different paradigms where we've changed subtle properties of the task. The prefrontal cortex, we generally do find effects, but they seem to be, the direction and the nature of those effects seems to vary depending on the task properties. So the exact involvement of the prefrontal region, I'm a little bit less sure on, but the SMFC seems to be very consistent. So in short, yes, we can modulate decision strategies with tDCS. and SMFC stimulation in particular seems to reduce caution. We use the same reference electrode for both those montages, the right orbital frontal cortex, so whilst we can't rule out that it's having some interactive role, it doesn't seem to be driving these effects. We only use cathodal stimulation. Others have tried anodal stimulation and they've found no effect. So again, I wouldn't want to put too much weight on that, but this does seem to be a cathodal-based effect here. So we want to move on to think about what the role of baseline neurophysiology may be in decision strategies. And particularly today, I want to talk to you about some DTI work we've done. So we collected baseline DTI scans as part of another really large study in the lab, and we re-recruited participants. We managed to get 38 back to complete our SAT task with stimulation. All participants completed 3 conditions, order counterbalance, so they came in for a prefrontal stimulation session, SMFC stimulation session, and a sham session. And we can correlate the degree of caution or discriminability shifts with instructions. These are referred as adjustments in performance, with the effect of stimulation on these and baseline measures of DTI structural connectivity. So this is just the effect of stimulation again. You can see on the left the difference in caution between active and sham, and again we find that the SMFC has reduced caution, and again we find that that interacts with instruction, so its largest effect for the accuracy focus condition. We now find, as I mentioned, the prefrontal cortex is a little bit more flighty in what it looks like. Here it's also reducing caution, but it was less so than the SMFC stimulation. We also found, again, some differences in discriminability, which was fairly consistent with what we'd found previously. So we can look at changes in caution or threshold with instruction for sham stimulation only and how that correlates with our DTI measures, the difference in the effective instruction across active and sham for PFC stimulation, and the same for SMFC stimulation. And then, of course, we can do that for both caution and discriminability. So this is the approach we took, and we did multiple comparison corrections, etc. So we focused on 6 particular tracks: the SLF1, SLF2, we had striatal frontal orbital, striatal prefrontal, striatal premotor, and striatal parietal tracks. Our thinking here was that we have good evidence that the frontal cortex is likely involved in these decision strategies, and we also believe the striatum is playing an important role as well. For each of those tracks, we broke them into 7 components. We had at 70 quite a good resolution of the tracks, so we decided to choose 7. It was a little bit arbitrary, but it was a factor of reducing the complexity of the data, given the number of correlations we wanted to look at, but also retaining some specificity of it as well. And we had measures of FA, which is tract coherence, and also radial diffusivity, which is indicative of the degree of myelination. So these plots are the simplest way that we could find of representing this data. So on the x-axis, you have the segment of each tract from 1 to 7. And on the y-axis, you have the different tracks. And it's just showing the correlation strength with, in this case, change in threshold on the top and change in discriminability on the bottom for the sham condition. So this is, in the absence of stimulation, what regions are correlating with tract strength for the SAT. And we find for changes in threshold, particularly the SLF2 in the left hemisphere seems to correlate, particularly at the parietal end of the tract. And for change in discriminability, we find that it's the striatal frontal orbital, left and right, and also the striatal prefrontal in the right that seems to be playing some role in individual differences in how well people adjust their thresholds and discriminability. In terms of the effect of stimulation, for prefrontal stimulation, we found a fairly specific effect. So it was the SLF2 in the left hemisphere again that seemed to be involved, particularly the level of myelination, in changes in threshold with instruction and with stimulation for prefrontal, but nothing relating to discriminability. So that one was quite specific. For the SMFC stimulation, we found, again, the same track but in the right hemisphere for the change in threshold. But for discriminability, we found a number of regions, largely striatal-based, generally more at the striatal end of the tract as well, that seems to relate to the stimulation effects on discriminability. So in sum, frontal parietal and cortical striatal tract coherence and myelination were related to the SAT performance and the influence of stimulation on performance. In general, less myelination and less coherence was associated with greater susceptibility to stimulation. For SMFC stimulation, this was generally right lateralized and more in cortical striatal pathways, particularly the striatal ends of the tracts, and for prefrontal cortex stimulation, this was specifically in the left SLF2. So we have pretty strong causal evidence across the studies we've run in the lab for the SMFC and to some extent the PFC playing important causal roles in the SAT. But these effects were largely on caution, but also to some extent on discriminability. We found that baseline white matter connectivity relates to SAT performance and the stimulation modulation to the same. And I think this is giving us some insights into why people's response to stimulation can vary, because we're finding that there are these baseline differences in neurophysiology which will relate to how effective the stimulation is to modulate this task. And this might be quite useful, not just for understanding the SAT, but also for thinking about applications of stimulation, both clinical and non-clinical. Our lab's also... Our lab's also done some work using other measures as well, so I'm happy to talk about those more at another time. So just to end with thanking those involved, I won't read everyone's name out, but in particular, Timothy Ballard and David Sewell did a lot of the computational modelling, and Joran Wards really led the DTI analysis.